which I do. Yes, it's actually doing us some good here. This is even better. I'd like to welcome people to our November 2nd colloquium. As you can see, we have reference to polls up here. The subject is discrete mathematics, and our local resident mathematician is going to tell us how to figure out what's going to happen at next Tuesday's elections based on polls, right? Is that... No, if we're lucky, he won't say anything about the elections next Tuesday. He will stay in the heady but fascinating realm of discrete mathematics and introduce us to his new textbook. Dr. Simonetti is a full professor of computer science, and he's the chair of math and computer science and business. And what? A wonderful husband, so I hear. I can't report on that from personal experience, but so without further ado, let me introduce Neil Simonetti.
So we'll get to the polls in a moment. Again, I want to thank the E.B. Glenn Fund. This was a fun project, and I really appreciate having support on doing this project. So thank you so much for that opportunity. So, shall we dive in? I know what you're thinking. What distinguishes math at Bryn College? Isn't math just math? Well, Swedenborg talks a lot about use. In fact, you'll find the word use almost twice as often as you'll find the word wisdom in the writings. So, Swedenborg makes strong mentions about how important that is. That which is without use can have no life in it. Not just a little bit of life or less life, no life. Love and wisdom without use pass away like winds. So the idea of what can I do with this mathematics, that's the emphasis that makes it distinctly Bryn. So let's talk a little bit about what's in this thing. After an introductory chapter on preliminaries, I have 8 chapters. And the first 4 make up our Math 101 course. It turns out that it was 2 years ago that I gave a colloquium on that material. And that's currently in our Math 101 course. It does a lot of continuous topics, from word problems and unit conversion to loans and interest and some statistical reasoning. So what I want to focus today's colloquium is what's in the second half of the book. I actually wrote more of this part first before I wrote the first half. Because before we created this Math 101 course, I used to teach a course called Math 135, which focused on the discrete topics in this book. And so I actually wrote some of that part long before I wrote the first few chapters, not knowing I would have a textbook at the end of when I first started. So I want to talk about what's in that second half. I'm going to be hopefully taking over the Math 102 course, not this coming winter, but the following winter, and using a lot of this book to teach that course with. So I'm looking forward to getting to use that second half more. Right now, it's only getting used in a little bit of our upper-level discrete structures course. So that second half hasn't got as much play as the first half of the book in the last several years. So let me tell you about what it's like teaching that material in that second half. This is the part on combinatorics and probability. Combinatorics is a graduate-level word for counting. It doesn't sound very impressive to say counting, so I studied combinatorics in graduate school, not counting in graduate school. What makes it challenging to teach is that some of the concepts are very intuitive, and some of the concepts are not at all intuitive. And so the key to keep students from constantly second-guessing themselves is to have them figure out when is the intuition going to work, and when do you have to use a more complex model? So that's the trick that I've found that can make this difficult to teach well, and if you can get students a feel for when the easy approach works and when it doesn't, you can have success. So here we're going to try some poll EV. So if you have that web address in your smartphone, here goes the first one. I'm going to activate this poll. So you should now see, if you're logged in on your smartphone, the question of what is the probability of rolling a 4 on a 6-sided die? So if I roll this die, what is the chance? And I've already got 4 responses I see. They're coming in. Let me try it now and see what it is. Ooh, what did I get? Oh, I got a 1. Must be 0%, because I'm just never rolling a 4 here. So I can see, we got 8 people responding. So yes, this is pretty intuitive, wouldn't you say? So what's intuitive about this? Well, if you have equally likely outcomes, so we're assuming that this die is fair, if I have 6 possible outcomes, each outcome should happen about 1 in 6. So that's pretty straightforward. Let's try this next one here. What's the chance of rolling a 4 or a 5 on this die? Ooh, getting harder now. So I want to roll a 4 or a 5. Well, I've got to activate this one again. Let's see, is that activated? Nope. Now it's active. No. Try again. There we go. So go ahead and give me your answer. So what's the chance of rolling a 4? What did I get, by the way? Where did that die go? Oh, down there? I got a 1 again. Oh, not very good at this. Get that. So, okay. So again, this is still pretty intuitive here. So if I have events that do not overlap at all, mutually exclusive, if I know the chance of each one is 1 in 6, the chance of getting one of those 2 is 2 in 6. So far, our problems haven't been that nasty. Let's try this one. And this time, I'm not going to let you see what your friends are answering first. So you're going to have to figure out, without seeing what everyone else answers, what's the probability of getting double 4s when rolling 2 dice? So I can see total results on the bottom there as we're at 1 right now. So I'm not going to show you the answers until after I got a bunch of results in. So what's the chance that I roll double 4s? I can roll my 2 dice. I can't believe it. I just rolled double 4s. Must be 100%. Take a look. I rolled double 4s. Incredible. Well, we're about to find out. So how many answers do I have in here? I've got 7 answers. You want to see what the poll results were before I show the answer here? Okay, let's show the results. So I'm getting, let's see. Oh, I should be not hidden anymore. Let's try it again. Oh, but rolling double 4s. That's the one. Click and click. And it's not working there. Well, I can tell you that I have 1 person who said 1 in 6, 1 person who said 1 in 12, and 5 people who told me 1 in 36. I don't know why it's not showing. This worked last time. Try again and show. Okay. Well, little technical difficulty. Sorry, I can't show you those results. I just went forward a slide. Okay, so yeah, I ran through this several times and I never had that problem before, so I'm not sure what the issue is. But the real answer is 1 in 36. And one way to look at that is that for every 6 results on that red die, I have 6 different results on that blue die. So there's actually 36 ways I can roll those 2 dice, which gives me a 1 in 36 chance. Once you look at it that way, it still has some intuition left. I've got a couple more difficult questions for you. They're going to get a little trickier now. So what's the probability of rolling at least 1 4 on one of the dice? So a 4 on the red die or a 4 on the blue die. So go ahead, give that an entry. Tell me what you think the chances are. I've got no results in so far. Is it not active? It's not active. Let me make it active for you. Oh, come on. Probability of rolling at least 1 4. There it goes. You should now be able to access that. I've got one result in so far. Anyone else want to make a guess? Go ahead. Enter your guess. 2 results in. 3 results coming in. Fast and Furious 4, 5. All right, let's see if I can view this poll. If I click that, it should make it visible. And it is not. Let me try if I go this way. Okay. Oh, that's why it's not doing it. I'm not logged in anymore. That solves that question. Oops, I just advanced the slide. All right. I got to log in. Oh, come on. There we go. I see people changing their answer. No fair, no fair. All right. Got to see this. Wouldn't you like to know? I think it's that. All right. So I did see a bunch of answers congregating to option C, but that should tell you why it's not intuitive. So what's going on here with this one? And please advance. There we go. Again, a lot of people might be inclined to think, well, there's a 1 in 6 chance for the 4 on this die, a 1 in 6 chance for the 4 on this die. Why shouldn't it be 2 out of 6? And the figure, it really illustrates why that's not the case, because you've counted the result of double 4 twice when you count that way. So I have to subtract off once the chance of rolling those double 4s, and that leaves me not 12 out of 36, but 11 out of 36. So the intuition's starting to get tricky here, but you recognize, oh, when the events can overlap, I need a more complicated formula to answer this question. I've got one more poll EV for you. You live in a town of 10,000 people. 1% of the population has a disease. Suppose the disease has a test that is 98% accurate. So if you have the disease, it'll tell you 98% of the time that you have the disease. And if you don't have the disease, it'll tell you 98% of the time that you don't have the disease. If you test positive, what's the chance you actually have the disease? And I believe it's active now because I've logged in. So you should be able to answer that. Is it active? Yep, I'm seeing responses. They're coming in. So what do you think the answer is? Once I get more, I'll reveal. And we'll have I got 5 results in. Anyone else want to answer? What do you think the chance is? If you test positive, what's the chance you have that disease? What are we up to? 6 responses? Anyone else willing to go on a limb? All right, let's take a look. So people went for, there we go. Oh. Looks like people went for the 98%. Some people got suspicious going, it couldn't be that easy because he was saying it was a hard problem. So we got answers all over the place here because people are getting suspicious. All right. So what's the answer? What? 33%? How's that work? If you're curious about the formula and where it comes from, buy the book, section 6.5. But to illustrate the problem, just look at the bottom half of this slide. So you have 10,000 people, 100 have the disease, 9,900 don't have the disease. Of the 100, 98 test positive, 2 test negative. And of the 9,900, 98% test negative, and 2% of that 9,900 test positive. So of the people with the positive test, only about a third of them actually have the disease. So if all you know is I have a positive test, there's still a better than 2 to 1 chance that you're free of the disease. Very unintuitive, but that's the way probability can work sometimes. So sometimes it can be very surprising, and sometimes it can be very intuitive. So I always love this example because it really doesn't make sense until you really dig deep into the numbers to see why that number should be 33%. Yeah. Well, if there's no indication of who, if they choose to test randomly, you're still okay. If they choose to test a segment who show a symptom, that's a different matter. So if I see a symptom in people and only test those, then these numbers change. But if I just test randomly, it's going to be that percentage. If I only test you and know nothing else, the chance you have the disease is still that same probability. So I like to go into expected value in games to really get some probability concepts across. So imagine this game. I have 8 cards with numbers from 1 to 8 on them, and they're winning cards. And I have 4 cards with numbers from 9 to 10 on them, 2 9s and 2 10s. Those are losing cards. So you get to pick a card at random, and if you draw a winning card, you win that amount. If you draw a losing card, you lose that amount. Should you play? And by should you play, I mean, imagine if you played 1,000,000 times, would you expect to make a lot of money? Would you expect to lose a lot of money? Or would you break even, do you think? So who wants to play? Who wants a card? I'm not offering any money, unfortunately. But what do you think? I don't have a poll for this one. But what I mean, it's true that I have twice as many winning cards as losing cards. But when you lose, the amount's a little higher. So what do you think? You think I'm good playing this game? I'll eventually come out ahead? No. Yeah, okay, we have someone who thinks that they're... If the casino's offering the game, it's probably trouble. Well, let's look at the analysis here. There's a 1 in 12 chance of drawing each card if I shuffle it properly. So there's a 1 in 12 chance I win $1 and a 1 in 12 chance I win $2. In the case of drawing a 9 or a 10, there's a 2 in 12 chance that I'll draw that number. And if I add up all of those weighted probabilities, I end up losing about 17 cents every time you draw from the deck. So no, you shouldn't play this game if you want to make money. So then I have a project in the back of this chapter that talks about calculating expected value from casino games. So you're on the roulette wheel, and you can bet on red or black. If you bet $1 and your color comes up, you're paid $2. If your color doesn't come up, you're paid nothing. So let's look at the calculations here. There's 18 red squares, 18 black squares, and 2 green squares on that roulette board. So there's an 18 out of 38 chance that your color is going to come up. That means there's a 20 in 38 chance it's not. And if I calculate those weighted probabilities, I'm getting back about 95 cents for every dollar I bet. That means every dollar that's bet in the casino, they're making about a nickel. So they want lots of bets. They want lots of high bets because they're making 1 nickel off of every dollar that's bet on that game. And that means, on average, you're losing a nickel for every bet you make on that game. Here's another example. Got these lovely props here. Dealer has an ace showing and you're playing blackjack. You can take insurance in case the dealer has a 10 card waiting behind. And if you take the insurance, and in fact the card is a value of 10, you get $2.50 on that $1 bet. Should you take the bet? Well, assuming we have a large shoe of cards, so that each amount is about equally likely of coming up, there's 13 different card values, and 4 of them are 10s. The jack, the queen, the king, and the 10. So the chance of getting paid off is that 4 in 13 times 2.5. I'm getting 77 cents back on every dollar I bet on insurance and blackjack. So you'll lose your money a lot slower betting on roulette than you will on blackjack insurance, but you'll lose your money either way. So I love these illustrations that really show how these calculations work. This same idea can be applied to buying warranties or insurance. If the casino's offering the game, you can be pretty sure they're going to be making a profit whenever it's played. If a company's offering you an extended warranty on a product, you can be pretty sure they've priced it in a way to make a profit on that warranty. But there is a small exception to that. If you have information that the people making the odds don't know about, that can change the game. So my wife and I bought a projection TV about 10 years ago. We got a discount because it was one of the floor models they used to display. And the cashier said, this was a display model. It's been projecting for weeks. Get the warranty because the bulb will likely burn out before the warranty expires. I took his advice. I got the warranty. Sure enough, the bulb burned out while the warranty was in effect, and I got the free replacement bulb. So because I had additional information, that was actually a case where getting the warranty was in my favor. A couple months later, Circuit City went out of business. So I'm glad I got the warranty just before that happened. I don't think that was the reason they went out of business, but I was interested that there are some cases where you might have information that does make that worthwhile. But in general, if they're offering you that extended warranty, you probably don't want to take it. You still might want to insure things that you can't afford to replace, like your house, but probably better off not getting it on your toaster. All right, so all of these probabilities and casinos are depending on randomness and the rules of randomness. But does randomness even exist? Right, what does Swedenborg say about this? Well, Swedenborg does say that divine providence extends to the smallest details of a person's life. So even what number comes up on this die is being watched. And Swedenborg has a great memorable relation about him playing a game of dice and spirits talking to him about how fortune and chance works. And they could see whether he was about to win or lose based on whether he had a bright cloud or a somber cloud near him. So you can imagine if you could have your spiritual eyes opened and you were to go to a casino, you could make a lot of money because you would have that information. By the way, I did a little digging, and around the 17th and 18th centuries, there was a very popular dice game called Hazard. It's actually mentioned in the Canterbury Tales. I don't know if Athyn can verify that. But yes, it's a forerunner to craps. It's actually a more complicated version of that game. It was played a lot in the 17th, 18th centuries. It was played a lot for money. And people must have been losing so much money that that word hazard now has a different meaning to us as a dangerous obstacle that should be avoided. That wasn't its original meaning. It was just the name of this game. But it's become that meaning because this game was so detrimental. So I thought that was interesting when I was looking that up. So if divine providence goes into the minute details, why do the laws of providence obey these laws of probability and statistics? Shouldn't they let the good guy win? You know, when Han Solo was quoted that the odds of navigating that asteroid field were 3,720 to 1, he forged ahead into that asteroid field. And as a movie watcher, you probably weren't too concerned because you know it's a movie. So why shouldn't divine providence do the same thing for us? Right? Well, divine providence pays no attention to what goes on that swiftly passes. It doesn't say a little attention or less attention, no attention. So it has no stake in what I roll on this die roll, and it has no stake in the result of the Eagles game this Sunday. It doesn't care about those kinds of things. It will make sure that something good can come out of those, but as far as affairs that swiftly pass away in this world, no attention at all. So what's the harm in having the good guys win a little extra? So if divine providence didn't follow these rules of stats and probability, it would provide us with some external proof that divine providence exists, and external proof of a creator. What's so bad about that? Right? Wouldn't that be bad? Wouldn't that be great? Well, not so much, because the state of freedom that we're in to allow us to logically choose to deny God or accept God is essential to our reformation. If we had an external proof of God that God had to exist, you don't have the option to not believe in God. So you have to have that freedom. That's a high priority. And so the laws of probability are followed, and bad things can happen to good people, unfortunately. Because this freedom is far more important than you hitting the jackpot when you're playing a game. So that's why it seems like the bad guys are allowed to win in this world. Kind of depressing, but at least it makes sense. I don't know. Let's move on to the next chapter here. So logic. This is chapter 7 in the book. Understanding logic can be useful to isolate simple systems in a complex system. It can help you identify critical links in processes, and perhaps my favorite is expose invalid reasoning. I know you've seen lots of political ads, and I'm sure you've seen lots of examples of invalid reasoning. The key I find to illustrating these topics are to illustrate the concepts using puzzles. Because students tend to love those kinds of puzzles. So an example that for a logic device is a Venn diagram. So a Venn diagram just simply indicates here are ovals representing sets of objects, and you can overlap those ovals to indicate items that might belong to both sets. So the things inside both of these ovals are things that are both green and edible. And I apologize if everyone doesn't like Jell-O, but I have Jell-O in there. I have things that are green that are not edible in the green circle, not in the brown circle. And I have things that are edible that are not green, that are inside the brown oval and not inside the green. And things outside both are neither edible nor green. And I can have illustrations where you might have one oval inside another. So if I accept as truth that all trees have roots, I actually draw the tree oval inside the root oval. And what that tells me is, if I know something is a tree, so here's Elmo the elm tree, because it's inside the inner oval, it's also inside the outer oval, so I can conclude that the elm tree has roots. And that's valid reasoning. Similar, if I start with the premise that all trees have roots, and I say a dog doesn't have roots, let me check. Yeah, I don't see any roots. So he belongs outside the brown circle, and if he's outside the brown circle, he's also outside the green circle, so therefore a dog is not a tree. Where this gets into problems are when you try to make reasoning this way. The polynomial x squared minus 5x plus 6 has roots, therefore it's a tree. Doesn't work because this diagram shows you that things can have roots without being a tree. So again, this example only has 2 ovals. In the book, I've got examples with 5, 6 ovals in them, and they all overlap in different ways. Then you have to figure out if the reasoning is valid. And if you draw the diagram, it's a lot easier to follow what's going on. The other elements I have in the book are logic puzzles. These are very popular on the GRE exams. So if you've taken that graduate record exam, or if you're going to, you'll probably be practicing on these kinds of problems. So here I have Allie, Beth, Chloe, Dot, and Eliza running in a race. And I got to figure out what order they finished in. So what do I know? I have Eliza did not finish second, Chloe finished first, Dot finished ahead of Beth by more than one place, and Allie did not finish next to Chloe or Beth. What piece of information there do you think is the most useful? What's giving you a lot of information on that list? Yeah, the fact that Chloe is first, because it not only tells you who's first, but it tells you that no one else finished first, and it tells you that Chloe finished in no other place. So that one statement actually gave me 9 pieces of information. So that's pretty powerful. You compare that with the fact that Eliza didn't finish second, that only gave me 1 piece of information. It's still useful to add, but the positive information is much stronger than the negative information. So now I have to look for implied information. Let's look at that next requirement. Dot finished ahead of Beth by more than one place. So Dot can't be last because she finished ahead of Beth, and Dot can't be second last because if Beth were last, she'd be next to her. So I know that Dot can't be last or second last. Similarly, Beth has to be behind Dot, so she can't be first or second. But since Chloe was first, the best Dot could do is second, so Beth could not be right behind her in third. So I know that Beth is eliminated from second and third place. So I got all those 4 pieces of information from simply knowing that Dot finished ahead of Beth by more than one place. I also know that Allie didn't finish next to Chloe or Beth, and Chloe finished first, so Allie's not second. Is there anything now that's obvious on this table? Yeah, only one choice for who finished in second. Because it wasn't Allie, Beth, Chloe, or Eliza. It has to be Dot that finished in second, which means that Dot didn't finish third. So we're getting along this problem pretty fast. I no longer have anything really obvious. So what you often need to do in these kinds of problems, and this, for any of you who have done Sudoku puzzles, you've probably experienced this, where you have to try something out. You play what if. What if this happens? What's going to happen? So I've noticed that Beth has to be fourth or fifth. So what happens if I put Beth in fourth place? So that means no one else finishes in fourth, and Beth is not in fifth. Can I place Allie and Eliza? Well, I'm either going to finish the problem by solving it, or I'm going to find a contradiction. And that last requirement that Allie did not finish next to Chloe or Beth means that I'm stuck, because if Beth is in fourth, no matter where I put Allie, fifth or third, she's going to be next to Beth. So I can't put Beth in fourth. As I put her there, I can look ahead and see, no, that doesn't work. So I have to erase those temporary markings and put Beth in fifth instead. And there she is in fifth, which means no one else finished fifth. And now I only have two left to place. The fact that Allie's not next to Beth means Allie has to be third. And that puts Eliza in fourth. I've now solved the problem. So yes, when I teach this one, students tend to love these problems. I remember having a test problem on the Bryn Athyn monorail, which order do the stops happen in, and I would have information about the college buildings. So if you ever have a monorail, I'll let you know which order to put them in. So why is logic important? Certainly many people have a lot to gain by convincing others to support a policy, or a candidate, I suppose, or purchase a product or service. You know, no toothpaste gets teeth whiter than our toothpaste. Please buy our toothpaste. If they can convince you to buy their toothpaste, they can make a lot of money. So they're going to work on persuading you, whether it's logical or not. And Swedenborg certainly talks about this. Sense-centered people. Sense-centered people are people who only believe what their senses tell them and nothing higher. They can still think logically, and some of them actually with more skill and penetration than other people. So some of these people who only believe in their senses can wield logic really well. They know where fallacies are. They know how to persuade you. And so you need to be able to identify when they're pulling the wool over your eyes. So it's really important to have a good grasp of logic so that you don't get swept up in some field of advertising or political ads or whatever it is they're trying to do. So it's a really good skill to have, to be able to look critically at situations and identify when they're trying to persuade you of something. The final chapter in the book is on graph theory. This is a colloquium I gave a year and a half ago, where I talked about the college class scheduling algorithm, which I was able to put as a small example as the project of that last chapter. So if you're curious how I schedule college classes, look in the back of the last chapter and you'll see an example that talks about that. But I'll talk a little bit about finding perfect matchings in a graph here. The key to my teaching graph theory is to let students feel like they're looking behind the curtain, because there are some graph theory concepts that really have some simple principles, but they're not always obvious right at the start. So if I can give the students the feeling like, ooh, I get to see the secret behind how this works, that can get students excited to learn all about these processes. So here's a problem called a perfect matching problem. I have 5 professors and 5 classrooms. So I need to put each professor into a classroom. And Dr. Abel is content to teach in room 1, 2, or 3. Dr. Bear will teach in any room but room 4. Dr. Cole likes room 2 or 4. Dr. Davis is only willing to teach in room 4. And Dr. Earl has some weird phobia that doesn't like odd numbers. So the question is, can I assign everyone to a room? So I can draw a graph here. I can put professors on one side, rooms on the other, and I can draw lines connecting professors with the rooms they like to teach in. So I'm looking for a selection of edges that match up professors to rooms such that everybody gets a room. Is it possible? Or are we going to have a problem here? What do you think? Is there a way to match everyone up to a room, or am I going to run into problems? Can you see that chart? What do you think? If you find a solution, it's done, but how do you know when to stop looking? How do you know when, okay, it's not possible? Is there anything that'll give away the fact that something's preventing you. The fact that no one's raised their hand yet must mean it's impossible. Does anyone see why it's impossible? I'll give you a hint here. I can find a set of vertices, that's Cole, Davis, and Earl, 3 people, who together have only 2 rooms they like. So I can see on this graph that these 3 people can't fit in those 2 rooms. So there is no perfect matching in this graph. It turns out that if a graph doesn't have a perfect matching, it will always have one of these sets. So this condition is not just necessary for failure, it's sufficient, which means if you never find a set whose neighboring set is smaller, you will always be able to find a perfect matching. So this is the equivalent condition. That is, if no set has a smaller neighboring set, you will be guaranteed to find a matching in that graph. So that's one of the examples I have in my textbook on graph theory, where the secret is this idea of looking for a neighboring set that's smaller than the original set. So that's what I have to say. I'm only happy to take questions. If you can't think of any good questions, I've got some funny samples up here. So yes. Oh yes, with the microphone.
Hi. So many years ago, I taught a course called Finite Mathematics, and I used several different textbooks, and they all placed the chapter on logic before the chapter on probability for a variety of reasons, but probably one of them was that they could introduce Venn diagrams and the logic thing, and then Venn diagrams could be used for counting when you got to probability. So what motivated, if anything, your choice to reverse that order?
Well, I wanted logic before graph theory because I used the logic to prove the graph theory. I haven't found myself using the logic principles of my book to prove the items in my probability section, so I feel like I didn't need that. People have an intuition about how these numbers work already, and I wanted to build off of that intuition rather than building off the logic section. And I can certainly, when I teach the logic, I can talk about what we did in probability when we go back to that. So I dove into this first, partly because it was a way to get students an easy ramp up, because I find the beginning of chapter 5 is very intuitive and feels easy. It's a way to set your foot in, dip in, and it works on what's the chance of rolling a 4. And people like the feeling of, oh, I know what's going on. And then I gradually make it more difficult. So that's how I ended up doing that.
Yeah, so just one little comment on that probably supports what you were saying. I used to find that students didn't like the logic very much compared to other topics. And I think I ended up with a textbook that didn't have logic or made it kind of a optional chapter. So I think probably your choice was a very good one. Logic is, there are certain things in logic, as you well know, that really are very counterintuitive. And so, yes, I think you did the right thing. Yeah. But
I do have De Morgan's laws in the book. I don't always cover them, but they're in there.
Yeah, well, good.
But yeah, the logic puzzles tend to go over very well. It's a nice dessert to that chapter because that's what students love a lot. Oh yes, go ahead. Once you got the microphone, go ahead and ask.
I actually wanted to know why you decided to put Swedenborg quotes into the math book. Were you taking the quotes from his theological works, or were you taking them from his math and science works?
These are from his theological works. He talks about every subject in those works if you look hard enough. And so the fact that Swedenborg has a good explanation for a lot of what we see that most religions don't necessarily explain very well was really one of the appeals of this.
And so did you decide that just because you work at Bryn Athyn?
Well, I work at Bryn Athyn because I decided that. I don't know which comes first. I chose to work at Bryn Athyn because I like what Swedenborg has to say. So even if I worked somewhere else, I might want to put that in there, although I imagine if I worked somewhere else, the dean might not be happy with that. So I'm happy to have found a place where I can put that in and no one's going to complain at me. Any other questions? You want to see a weird probability example? I've got one. I know I had a question down there too. Okay, so Grace was asking me, could I see that weird probability example that I'm talking about? Because I have one on the next slide. Should I take Ethan's question first? Okay. All right. So here's the weird example. This is not in the book. I had it in an earlier version of this slide presentation, decided not to put it in there. But this is really weird. So here we are at the Science College of Make-Believe University. And the graduate school is facing criticism because a lower percentage of female applicants are being accepted into their programs. So in this case, we have 50 male applicants and 50 female applicants, and 30 of the men were accepted into programs, and only 24 of the women were accepted into programs. So, okay, let's break it down by department and see what happened. Let's look at the physics department. So in physics, 10 men applied, 7 got in, 4 women applied, and 3 got in. Higher percentage for women. Let's go to the chemistry department. 20 men applied, 16 got in, 6 women applied, 5 got in. Higher percentage for the women. Let's look at the biology department. 12 men, 4 get in, 16 women, 6 get in. Higher percentage for women. Let's look at psychology. 8 men applied, 3 get in, 24 women applied, 10 get in. In every department, women got in a higher percentage. And overall, men were in. What happened here? So what's going on? Why is it that every department favored women over men, and overall, men are being favored over women? And the numbers do add up. And you have a comment to make. Wait. Take the mic.
All right, I have a guess. Is it because women are applying to majors that are rejecting people more?
Yes, it's more, the biology and psychology are more competitive programs for whatever reason. And so this means it's possible to have graduation rates in a school district go down, and when you look at each school, the rates could be going up at every individual school. Things like that are possible. They're weird, and they can happen. So I love examples like this that really show you there are some very unintuitive things that can happen in probability. But if you could look at those over and over, something has to be done, and you look at each department, and every department's looking.
Oh, wait. Oh.
Well, what's useful is you can look at the result and not assume something is necessarily wrong. Because every department's being fair, but yet the numbers look like there's something unfair going on. So if I want to get you in trouble, I'll just quote the big number, if I have an axe to grind with you, and I'll say, hey, look, you're in trouble, you should be fired. And you look at each department and you're going, no. But, public opinion only looks at the big numbers, you could be in trouble. So being aware of this can hopefully diffuse some of that trouble. I don't know. Yes?
So then, do schools often accept more men because they know that the women will, I guess in this case, tend to be accepted into the majors more? So then you kind of accept more men because you expect that a few of them will drop out or not continue?
This is probably a case where the departments have no knowledge of what other departments are doing. Every department is acting individually, and the group behavior becomes weird. But the individual departments are simply taking the best candidates. And both women and men are being similar probabilities here. But because of the way the applicants spread out, it looks like there's a pattern going on. But when you shine a light on it, the pattern goes away. So I don't think anyone's consciously trying to raise or lower any gender in this case. And again, this is a fabricated example of what could happen. I wouldn't say this is likely. This school must have a very strong chemistry department. They have lots of chemistry applicants. So who knows why? Maybe they have a star professor in chemistry. But again, this is made up data to illustrate a point about what's possible in probability. Other questions? For those of you who are here to get extra credit, I've got a sticker for you. For those of you that want to purchase a book, I've got a few extra copies for $30. And I will take that money back to the book room. So if you want a book, come on up. I'll even give you a signature in there if you like.
Okay, if there are... Oh, wait. We didn't get Ethan's question yet.
Oh, another question? Okay, Ethan, go ahead.
Wait, Ethan.
Wait for the mic. Here's the sticker.
So this book has some really intriguing foundational things in it. What would you recommend as the the lowest, the youngest comfortable age that you would recommend tackling this in? So would it be available for like an AP junior high school class? Would that be something that would be able to handle some of this, or only half the book?
Believe it or not, there's some of this that might even be accessible to sixth graders. It's really a wide variety. Now, generally this book is targeted at an audience who may have not gotten math the first time around. But the information on percentages sometimes appears in sixth grade curriculum. Now, there is some college level analysis attached to that, but some of the basic concepts do drill down to that lower level, because sometimes people need to be refreshed at that level. So I think there's a large variety of ranges that could get something out of this.
Do you have road signs that indicate this is the conceptual stuff, this is the difficult stuff, or this is the advanced material in the chapter, this is the
in each section I try to have advanced applications to them, but I don't usually warn a chapter, this is going to be harder than that one. I will say that in class. Mm-hmm. I think there's sometimes I might have a section that says this is extra or optional material, but for the most part, that's up to the instructor to tell them, hey, this is an easy part, this is a hard part.
But for somebody taking a high school class through this textbook, it would be, with a little prep, it could be easily navigable for age-appropriate.
I think there's part of it that certainly could be. Again, some of it might feel easy, some of it might feel challenging. I haven't tested that audience yet.
Well, I think with that question being finished, I'd like to close the formal proceedings and thank Professor Simonetti for his presentation.
Anyone still need a sticker? Well, I know who you are. There you go.